Hello guys, this is the Med Dude and today we're doing Chemistry Unit 2, January 2009, so let's get right to it. So, question number 1, 1A. So 10 centimeter cubed of 0.25 mole dm cubed of KOH solution was placed in a conical flask and was titrated. So, that's been titrated with 0.2 mole dm cubed of HCl solution, so AQ, using phenolphthalein. Okay, so that's an indicator, right? So phenolphthalein as an indicator. So what color would phenolphthalein turn at the end point in this reaction? So let's look at what's being titrated here. We know that phenolphthalein, right? So going to copy that. So phenolphthalein turns colorless in acidic solutions, right? So phenolphthalein, so in acid goes to colorless, and in basic solutions it turns pink, right? Basic solution turns pink. So what's happening? So the indicator in the base, right, should be pink, because we start off with, this 10 centimeter cubed of KOH, and then it's titrated, right? So in the conical flask, right, we have KOH, which is a base. So it should turn from pink to colorless. So it should turn from this to this, from pink to colorless. So that means that the end point, the end point should be colorless. So the answer is A. Alright, part B. The best piece of apparatus to accurately measure out 10 centimeter cubed is A. So we have the options pipette, burette, syringe, and measuring cylinder. So right off the bat, we should know that syringe is usually not used. It's not usually used to measure liquids, right? So it's already out of the equation. So this is gone because this is usually used to inject or draw fluid. So inject or draw fluids. All right. What about A, B, and C? A, B, and D: pipette, burette, measuring cylinder. So in terms of degree of accuracy, right? So if we draw something like this, we have degree of accuracy, like, so this, we will have low to the highest degree, right? The lowest degree of accuracy is obviously the measuring cylinder. It has a large increments, right? They're not very, you can't see from 0.1 to 0.1 centimeter cube, right? So the lowest one is obviously our measuring cylinder. So this is our measuring. I'm just going to write D. So D. What about the next one? Burette is pretty accurate, but only because it's a volumetric burette. So if you're 25 centimeter cube burette. On the other hand, pipette is the most accurate because you can account for every drop. You can account for every drop, which is usually like 0.1 centimeter cube. It's very accurate. It's very accurate. So the highest is A, and then in the middle we have B, because they're volumetric burettes. So this accounts for every drop. So that's the key thing. So the best piece of apparatus should be a pipette. All right. What volume of 0.2 mole dm cubed of HCl was added by the endpoint? So in order for us to find the endpoint volume, we know that at the endpoint both moles of, so both HCl and KOH, the potassium hydroxide, are equal, right? So if we find out the other, we can find out the other one, right? So we can easily find out the moles of KOH. That's going to be CV, right? So the equation N equals CV comes into play. So that will be CV. What's the concentration of KOH? They tell us it's 0.25 mole dm cubed. So this is going to be 0.25 mole per dm cubed times the volume. Now the volume has to be in dm cubed, so 10 over 1000. Okay, and then we have the moles of hydrochloric acid. So we know it's CV, we know the concentration is 0.2 times the volume. So all we have to do is now rearrange. So this would be 0.2 V equals, so you have our calculator, so it will be 0.25 times 0.1, 0.25 times 10 over 1000. That gives us 0.002. 0.25, 0.0025, yeah, so 0.0025. So V equals 0.0025 divided by 0.2, and put in the calculator, divided by 0.2, you get 0.0125 dm cubed. Now to convert dm cubed into centimeter cubed, all you have to do is times by 1000. So we're going to do this. So times by 1000 will be 12.5 centimeter cubed. 12.5 centimeter cubed. So this is the volume of hydrochloric acid that was added to the in the endpoint. 12.5. So that answer is C over here. Move on to question number 2. So which of these metal hydroxides is the most suitable in water? So in order for us to understand this, we have to look at which. So we have barium, right? We have barium hydroxide. Barium hydroxide. We have calcium hydroxide. We have magnesium hydroxide, and we have strontium hydroxide. Right? So if we go here, so we have over here. So if we go here, so this is what we've been given, right? So we have barium. We have barium, right? Try to reduce the size. So we have barium, we have calcium, strontium, and magnesium. So we're going down the group, right? What happens to solubility of these hydroxides as we go down the group? We know that solubility, so I'll write solubility. Down the group, what happens to it? We know the solubility down the group increases. So increases down the group. So if this increases, we need to look at the lowest in the group, the lowest element. So that's going to be barium. So that means that barium hydroxide is our most soluble in water. So the answer is A, barium hydroxide. Next, which of these metals give a lilac flame? So we know that sodium gives a yellow flame, and calcium gives a brick red, orange red flame, red. Potassium gives a lilac flame, right? Magnesium gives a white flame. So having this knowledge now, we know that they're asking for the lilac flame. So the answer should be C, potassium, because that's the only one that matches the question. Which of these is a tertiary alcohol? So this is 3-methyl pentanetol. So let's draw them. So if you're ever confused, just draw them. So we have. So let's draw A here. So A will be this. Wait, nope. And OH. So we have 1, 2, 3. 1, 2, 3. 1, 2, 3. Yeah, 3-methyl pentanetol. Sorry, no, not this one. This is not. Sorry. So here we go. Okay, so 3-methyl. So 1, 2, 3, and then you have a methyl group. Then you have OH, and then you have another. So this A, B, B is pentanol, so that's 1, 2, 3, 4, 5, and then you have the all pentan 2, 1, 2, so this is the all here. C, pentan 3 also 1, 2, 3, so OH here. And then D is 1, 2, 3, whoa, 1, 2, 3, 4, then you have the OH. Now, out of these alcohols, let's look at the alcohols we have. So this is a primary, so B, so this is primary, right? So you can see that B, this and this, they're both primary. They're both primary alcohols, so we can just cancel them, right? Next we have A and D left. A is actually a tertiary alcohol. Sorry, A is actually a secondary alcohol. So you can see here, this is pentan 2, also over here, these are two branching groups. This is secondary. The question is asking for tertiary. So we know that D is also out of the equation. So just by eliminating, we know that A should be the answer. But let's double check. Is this a tertiary alcohol? Let's see. Does it have 3 carbon groups going away? 3 are functions? Yes. You can see that the 3, so this is a tertiary alcohol. So the answer is A. Which of these statements about fluorine is not correct? Okay. So is fluorine a gas at room temperature and pressure? Yes. Yes, it is. Can fluorine react with chlorine? Can fluorine react with chlorine? Chloride ions. And does it form salts? It does. It does form salts, right? So that's also yes. It forms salt. Does it form salts with group 1 metals? Does it form salts? Yes, it does, because it has a F minus charge and group 1 metals have a 1. So M plus charge, so they form the compounds MF, where M is obviously a metal. It is less electronegative than chlorine. That is not true, because this is the most electronegative element in the periodic table. So we know that D is the answer. Question number 6. What is the oxidation number of oxygen in dioxygen difluoride? So we have O2F2. So we have O2F2. Now, which of these molecules takes priority? In such compounds, it's the most electronegative, so it's the most electronegative atom / element that takes priority. Takes priority. So that means that the most electronegative element takes priority, so that would be O2F2. So that means that we're going to take F2 as our -1 charge times 2, right? So we're left with O2. We don't know the charge of this, but it should equal, so this is 2 times whatever this charge is, it should equal 0 when we add them. So we can just construct an equation. So we can have 2x, where x is the charge of oxygen, plus -1 times 2 equals 0. We have 2x minus 2 equals 0. 2x equals 2. X equals 2 divided by 2, which is 1. So the charge, or the oxidation number rather, of oxygen in this dioxygen difluoride is +1. +1. So that means our answer is C. Alright, which of these molecules are polar? So we've been given PCl3, CO, CO2, and CCl4. Okay, so we have P. Let's draw these. So P, Cl, Cl, and Cl. So if I draw it like this, and if I give, so this is usually, and we have a lone pair here for PCl. Now for CO, we're drilling the pole, CO. CO is also polar. Let's do the CO2. So that's CO and CO over here. CCl4, Cl and Cl and Cl over here, and we have carbon monoxide. So carbon monoxide is also polar. This is a polar compound. Now, CO2 and CCl4 are not polar. And because they're not polar, they can't be in these answers, right? So you can get rid of CO2 and CCl4 because they're symmetrical and they don't have any bonding, any lone pairs, right? So because they're symmetrical, they're also non-polar. So that means that we can get rid of anything that has CO. So C is gone. Sorry, anything that has CCl4 and CO2. So CO2 is gone and CCl4 is gone. Now, and all 4 is gone because we know that this includes CO2 and CCl4. So our answer must be B, because PCl3 is polar because of the lone pair, and also there's an unequal charge distribution in CO. So B is the answer. 8. Which intermolecular forces exist between molecules of ethoxyethane? So we have instantaneous dipole. Okay, these ones are common for usually any molecule. Okay, permanent dipole. That's if they have a dipole. Okay. What else? If we know that if they had a hydrogen attached here, we could have said they have hydrogen bonding, but they don't. So we can't conclude that they have hydrogen bonding. So hydrogen bonds are gone. So we don't have that. Okay. Now what other things can we have here? So it's important to know that the hydrogen bonding is not present here because there's no OH group, right? So that just bear in mind when looking at other molecules and determining which IMF or internal molecular forces exists. So in this compound, you can see that this instantaneous dipole, induced dipole, is already present. It's in all molecules, right? So this is present. What about the permanent dipole? That's also present. What about the permanent dipole? That's also present. So you need to have all three for these for the IMF which exists between these molecules. So the answer is D. Question number 9. The following liquids all have the same number of electrons in each molecule. Which one is likely to have the lowest boiling point? Okay, you can see that this is an alcohol, right? So you can see this one is an alcohol. So this is alcohol. The rest we have to draw to find. They're most likely we can draw the rest, but they look like they're alkanes, but we can draw them. This is an alcohol. So we know that alcohol already has the highest boiling point, right? So highest boiling point. So it's already not, we don't need to consider A. Let's draw this. So this is 1, 2, so 1, 2, 3, 4, 5. So this is pentane. 1, 2, 3, 4. Nope. 1, 2, 3, 4, 5. That's pentane. So we have 1, 2. And then we have 1, 2. Then we have, what else do we have? Then we have let's see. Wait. Let's see if I've done this correct. So we have 1 carbon going this way. Then we have another carbon, 2, and then that has 2. And then we have this. And then this one is 1, 2, 3. 1, 2, 1, 2, and has another one there, and 3, 4. So these are the 4 compounds, right? Now the key thing here is that how can we tell which one has the lowest boiling point? Is because it's the one that's the most, that's not the most, I should put this, the one that's not the most stackable, if that makes sense. So basically what you need to know is it's the one that has the most branch chains. So the most branched molecule will have the lowest boiling point. Now why is that? It's because you can see here for B, right? You can stack all of these up. You can stack all of these up, and they have strong intermolecular forces, right? Strong IMF. As opposed to, let's say, C. C is a very, it's hard to stack a molecule that's this big. So you can't stack them the same way. So how would you stack them? It's hard to stack. So you can see there's a lot of space between them. So this is weak IMF, so intermolecular forces. And because there's weak IMF, we can deduce that it has the lowest boiling point, right? For D, obviously, the D option, you can still stack them, right? You can still stack them, but it's not as easy, but you can still stack them. It still has, so in comparison, this would be medium, or this would be, so if we name them 1, 2, this would be stronger IMF than 2. Okay, so that would mean the answer is B. Sorry, not B. The lowest boiling point would be D. Sorry, C. The most branched alkane. Alright. So which of these is likely to be a solvent for cyclohexanol? So you have water. Okay, right? So this is already two polar. So we can cancel that. So now this, what's B? B is propan 2, I think propan-2-one. Okay, so we'll see that. And then NaCl is not even this is not a solvent. And D, we have what? Hexane. So we have 1, 2, 3, 4, 5, 6. Hexane. Hexane isn't even hexane is non-polar. So would not dissolve cyclohexanol at all. So the only thing that would be similar in terms of polarity would be this. Similar in terms of polarity. So that's why B is the answer. Okay. The ability of a liquid to flow is linked to the strength of its IMF. Suggest which of these liquids flows the slowest when poured. Okay, so let's see what this would be, right? So this is butane, so 1, so let's draw them. So that would be 1, 2, 3, 4. That is pentane. That would be 1, 2, 3, 4, 5. Propan 1, 2 diol, so 1, 2, 1, 2 diol, 1 propan 1. So 1, 2, 3, and this has 1, 2 diol, so 1, so it has OH here, and it has an OH here. Propan 1, 2, 3 triol, 1, 2, 3, so 1, 2, 3. Nope. This would be OH, OH, OH. Now, if these liquids, same way they were stacked, right, in a liquid, you can see that the slowest to be poured out would be the ones with the strongest IMF. So the slowest would be the one with the strongest IMF. So that means we need to look at what type of bondings are involved. You can see here that this is butane and pentane only have the London forces and the London forces because they're not even polar, right? So the only London forces. But you look at B and A, you can see that they both have hydrogen bonding. Because you see the hydroxyl group, right? So that means we have to determine whether it's propane 1,2-diol or 1,2,3-triol. So it should be A because we have more OH groups, right? And because we have more OH groups, right? So this means that the attraction between the molecules of A would be greater. So this would naturally be more viscous. This is A. So the answer is A. Okay. So what type of species forms when a bond breaks homolytically? Now homolytically refers to what? This usually refers to the one-sided arrows. And what do we usually consider this when we're talking about free radicals, right? So the answer is free radical. Okay, question number 13. In the reaction between Ag plus ions and Fe2 plus ions, what would be the effect of increasing the concentration of Aq plus ions? Ag plus, sorry, not Aq, Ag, silver ions. When you increase the concentration, so we're increasing the concentration of Ag plus ions, right? We're increasing the concentration. Because we're increasing the concentration, right, that means that more of Fe2 is reacting with this. So you write more of Fe2 that is unreacted is reacting with Ag plus. So that means we're increasing the amount of both product, increasing the proportion of both products. And because we're doing that, that also means that we're increasing its yield. Yield is increasing. And because we're increasing the concentration, there are more particles, right? There will be more of the chemical present. So more reactants are moving together, which allow more collisions, right? So this allows more collisions, more successful collisions to happen. So that reaction rate is increased. So we know that, I'll write rate also increases. So the two things, rate increasing and yield is increasing. So let's look at the ones which have that increases the yield. So this is increasing yield, okay. Sorry, increasing rate. This increasing rate. This is decreasing rate, so it's already gone. So we don't, and this is increasing rate. So we're left with A, B, and D. Now we know that the yield increases. So A says it stays the same, so no. A is gone. The yield decreases, no. B is gone. We know the yield increases, so that's D. So the answer is D. Alright. Which of these reactions is not a disproportionation reaction? So in order to answer this, we need to know what a disproportionation reaction is. That's when usually where an element of a compound undergoes reduction and oxidation. So it's element of a compound undergoes reduction and oxidation, both. Okay, so let's see the species here. So we have 2H2O2 goes to oxygen and 2H2O. You can see here that the oxygen is reduced to 0 and it's also -2 here. So this is a disproportionation reaction, so we can cancel this. Now let's look at B. Okay, so what's happening here? You can see that O3 has the same charge, right, as 2-. This is also the same, so that's fine. Hydrogen is still H+, and this is also H+, that's fine. What about the sulfur though? The sulfur is what? Sulfur is at 0 here, but it's at +4 here, right? It goes from +4 and it's 0. So that means this is a disproportionation reaction. So B is out. What about C? You can see that the Br- ion is minus, that reduces to 0. So reduced to 0. And chlorine is 0 and is reduced to, so this one is oxidized. So this one is not reduced. It's like you gain electrons. Yeah, this is reduced to 0. And chlorine, what? Chlorine what? What about chlorine? Chlorine is now oxidized to Cl minus. So this is not a disproportionation reaction. So C should be the correct answer. Now let's look at D anyways. D, you can see that it goes from +1 to 0 and +2. So this is a disproportionate reaction. So 15. Molecules absorb I radiation because of what? So we know that for a bond to absorb in I radiation, there must be a change in the dipole moment during the vibration. Now, polar molecules have dipole moments, right? At any change, we know that in normal conditions, everything vibrates, right? So it has continuous vibrations like stretching, bending. So, but any change in the dipole moment through radiation would absorb its molecules. So this, we can only absorb the I radiation if and only if we change the polarity. They change their polarity. So if they don't change the polarity, we cannot absorb, the molecules cannot absorb I radiation. Question number 16. How many of the following will absorb IR radiation? So we need to know that nitrogen, right? Nitrogen and oxygen, they both do not absorb IR radiation. They do not, as they're not polar molecules. Okay, and they do not absorb IR radiation. But what is methane polar? No, there's not. The other three, so this, and this, they are polar, but they're very weak polar. So CH4 will be very weak polar. CO2 is very weak polar, but it's still polar. So you're left with how many? 1, 2, 3, which absorb I radiation. So that's 1, 2, and 3. The answer should be 3. Question number 17. So we have IR spectra can be used to follow progress of reactions with propan 1-ol and propan 2-ol. Some absorption ranges are shown by the chemical bonds in the IR spectrum are given below. So we have OH in alcohol, C double bond O in aldehyde, and we have C double bond O in ketone and C double bond in carboxylic acid. So let's see what the question is asking. To identify the formation of the product when propan 1-ol has been partially oxidized. The key term here is partially. Okay, now propan 1-ol, what type of alcohol is that? That is a primary alcohol. And what happens to primary alcohol when you oxidize it? What happens to it? It turns into a aldehyde. And if we oxidize further, so this is plus, let's say O, and oxidize it further, what happens to that? You get carboxylic acid. So in this case, we are partially oxidizing it, so we're only getting aldehydes. So we need to look for the bond, C double bond O for ketones, sorry, not ketones, aldehydes. Aldehydes, we need to look for that. So you can look for the absorptions in aldehyde. So the aldehyde, C double bond O stretching. So that is 2. So we're looking for B. Alright. Next, to monitor whether all of the sample for propan 2-ol has been oxidized, what can we look for? Now for propan 2-ol, what type of alcohol is that? That's a secondary alcohol. What happens to that? When we add oxygen, so we oxidize it, what happens to it? It turns into a ketone. Now the question is very tricky. They tell us that it's all, to monitor whether all of the sample. Okay, so suppose not all of the sample is oxidized, you will still get a ketone. You'll still get absorptions for the ketone. You get C double bond O, ketone. You'll still get this, even if not all of the sample is been oxidized. But if all of the sample has been oxidized, there must be a lack of what? The OH bond in alcohols. Because if all of the alcohol has been turned into the ketone, right? So if all of the alcohol has turned into this, right? If all has turned into ketone, that means you have no alcohol left, right? No alcohol left. That means that there is a lack of this, the OH. So we need to look at a lack of the stretchings of in the IR spectrum of OH. So what answers that? That's a lack of absorptions in the IR spectrum at 1. Okay, so a lack of no. Let's see the other options. A lack of absorption at 2. No, we don't need that. We're not making aldehydes, so 2 is out. We're not making aldehydes. What about absorption in IR spectrum 3? Are we making ketones? Yes, we are. But we already said we make ketones anyways. So even if all of them were not oxidized, this would already be there anyways. So what about 4? As absorption in IR spectrum at 4, we don't even make carboxylic acid. So this is already gone and this is already gone. Alright. So now we are at the questions about reagents, reactions, and some properties of. So question number 18. This question is about reactions and properties of some halogen alkanes. State the reagents and conditions needed to convert the following halogen alkanes into the named products. Alright. So 1 bromobutane. 2 into butan 1-ol. So let's think about it. So if we need to remove the bromine, right? Bromine atom, and we need to put it into another. We need to put what? OH group, right? The easiest way to do that would be to use a hydroxide. Now, which hydroxide would we commonly use? We can use sodium hydroxide, or KOH, right? What else? What else would we also use? These hydroxides in reactions are usually used with what? With a mixture of ethanol and water, and almost always you also have to heat it up, and in warm conditions, in warm temperature, say. So the 2 marks you'd get for would be NaOH, KOH, that's the reagent, and the condition is the mixture of ethanol and water. You don't need to put heat, but it's better if you put this. So these are your 2 marks. So these are your 2 marks, one here and one here. So 1-isobutane into butylamine. Now as soon as I see amine, I think of ammonia. I think of NH3, always ammonia. Now this halogen alkane turning into an amyl. Well, we're reacting isobutane with ammonia in a heated environment. Now we're reacting what? We're reacting, so our reagent. So we are reagent is NH3, right? NH3. Now obviously this is also usually an ethanol as well. So we can write in ethanol. What about the conditions? Now because we're reacting with ammonia, usually we need to apply what? Heat. So apply heat and pressure. Heat and pressure. So your 2 marks are the following. 2 marks are reagent and the conditions. Now, true chloropropane into a propene. So this is an alkene. So alkene. So this is a halogen alkane going to alkene. That's actually a dehydration reaction. Now the conditions for this are what? Usually we have to use a very concentrated. So concentrated hydroxide. So concentrated hydroxide. So in this case, let's say we use NaOH, or you can write KOH. Both are fine, right? Concentrated. So this is our reagent. reagent. What about the properties? Now, same thing as before. We said that it should be heated and dissolved in ethanol. So we can write conditions should be dissolved in ethanol and in warm room, so warm temperature, or apply heat. It's better. Let's write apply heat. So, and apply heat. So this is our reagent, and dissolve ethanol and apply heat. Chloroethane can be prepared by reacting ethanol with potassium chloride in the presence of concentrated sulfuric acid, right? So chloride. Okay. Explain why similar reaction using potassium iodide and concentrated sulfuric acid should not be used. So should not be used. So that's the key. So it should not be used to prepare iodoethane. So the key thing here is we need to talk about the difference between Ki and KCl, because the only difference here is the Cl and the I. We have replaced the chloride ion with the iodide ion, right? So the key difference here is that the Ci bond, right? The Ci bond, right? The Ci bond is the weakest amongst the other halogens, right? In other words, right, the iodide ions are easily oxidized, right? So because they're the weakest, so they easily break. So we can say that the sulfuric acid is strong enough, is a strong enough oxidizing agent to what? To oxidize the iodide ions into iodine. So the key marks are to say that sulfuric acid is a strong enough oxidizing agent to oxidize iodide ions into iodine. Now the question also says, they also tell us that you need to reject someone just saying oxidize iodine, because that's very vague and would not give you a mark. Because we're talking about why this similar reaction. What's the difference? The difference is that iodide ions are easily oxidizable. So sulfuric acid is a strong enough oxidizing agent to oxidize the ions. Okay. Part C. Give the systematic name. So two gaseous halogen alkanes. So two gaseous halogen alkanes we have that could be used as fire retardants have the structure formula CF2ClBr and CF3CHF2. So I give the systematic name for CF2ClBr. So let's draw it. So we have C, we have F, we have another F, Cl, and Br. So that's the compound, right? Now we always do what when we're naming such things is alphabetical. So we have fluoro, we have bromo as the suffixes, and we have chloro. So what comes before is bromo, B, so bromo. Then we have chloro. But what about the fluoro? We have two of them, so difluoro. And what type of compound does this remind you of? A methane, isn't it? It's one carbon, so methane. Okay, so draw the skeletal formula of CF3CHF2. So we have our first carbon. It has 3 fluorine atoms attached to it. That's our first part. Then we go across to our second carbon atom. It has 2 fluorine atoms. So that's the answer to this, obviously, bromochloro-difluoromethane. And this is the answer for this. This is this formula. Alright. So it suggests 2 reasons how these compounds can help put out fires. So what do you think these compounds do? So because we know that the CF bond is very, so we can say that CF bond is extremely strong, right? So can absorb the heat from the fire, heat from the fires. So we've talked about it's extremely strong. So what else does that mean? That means so no, not that means, and since CF bond is strong, if the CF bond is strong and it cannot react or it cannot be broken, it's hard to break. What does it make the molecule? It is strong, which makes the molecule unreactive. And another word, a better word to use for that would be inert. Okay, so the 2 points are that it can absorb the heat from the fire because it's extremely strong, and because it's extremely strong, it does not react. Okay. So 4 marks. Explain why fire retardants containing some halogenoalkanes such as CF2, ClBr are being phased out. So just why the scientific community still supports the use of what? Use of fire retardants that contain CF3 and CF3CHF2. Okay, so don't be put off by the 4 marks. So let's say we don't know anything about the question. Let's deduce what we can get. So the key difference here is that this has only fluorine. This has Cl and Br, right? So that's the key difference that we can see, that we can only see. So what can we see from this? We can see that we know that halogenoalkanes, right? That contain what? That contain chlorine, right? Chlorine. So chlorine can do what? Can release free radicals. Halogenoalkanes that contain chlorine can release Cl, free radicals, right? Now, why is that a problem? Because the chlorine, right? The chlorine releases what? Free radicals. This Cl reacts with the ozone layer, and because now it reacts with the ozone layer, what happens to it? Breaks it down, right? The ozone layer is depleted because of this. And what does the ozone layer do? It protects us from what? From UV light, from UV exposure. So we can say what? We can say the ozone layer depleted because of this. So UV becomes what? UV exposure is more and can lead to higher risk of skin cancer. Higher risk of skin cancer. That's usually what UV light we can associate with. So why is this much better than this? Why is this so much better than this? Right? So why is this better? Why? because we can say that the CF bond, so previously remember that CF bond is what? It's very strong, is strong such that it does not release, it does not, or not say it, you can say the compound, so that the compound CF3CHF2 does not release F radicals, free radicals. So this is very important, because at the end we do have to state why this is better, why scientists still support this CF3CHF2. So what are the 4 marks? You can say that chlorine releases Cl radicals, and because they release it, it reacts with the ozone layer, and because it reacts with the ozone layer, right, it is depleted. But more importantly, we have more UV exposure, which can lead to a risk. That is the main point. And the last one, which is very important that you have to mention, is the comparative. So this is this statement over here. Maybe I'll make it in another color. This is very important. So this over here, this is more important. So this is your other mark. So this is 1 mark. This is also 1 mark. This is also 1 mark. This is separate 1 mark. So you need to get this separately. Okay, so you can say this is the comparative. Like, this is important. All right. Question number 19. So we have 10 centimeter cubed of solution containing Cu2 plus ions was added to excess potassium iodide solution, and the following reaction occurred. What happens to the Cu2 plus in this reaction? You can see here that it goes from Cu2 plus to oxidation state of 0. So you can say, right, the easiest thing is to say that. So what I usually do is I do Cu, right, before reaction, oxidation state is what? Oxidation state is what? Is +2. After is 0. So you can say copper has been what? Has been reduced. Is there anything else we can say? We know that iodide ions have a charge of minus, right? But you can see here, this is copper is reacting with iodine and is not producing Cu(I2) as it should, right? Because it's +2 charge. So that means that copper now has a charge of +1. So we can say copper now has a charge of +1 at the end of the reaction. The end of the reaction. So the key thing here was to know that copper has been reduced, right? Because from +2 to 0. So you can see here from +2 to 0, it has been reduced, and that it now has a charge of +1. Okay. So all of the mixture containing iodine was titrated using sodium thiosulfate at a concentration 0.2, endpoint 12.75. So this is the reaction. The endpoint is shown most effectively using an indicator. State a suitable indicator and the color change you would expect to see at the endpoint. For iodine, the easiest indicator is starch. Easiest indicator. And what does it turn? It turns from blue black to colorless. Now, some people, according to the examiner report, try to use another indicator. They try to use methyl orange. And if you were thinking that, then it's very wrong. It's not correct for this question. The easiest one, the most effective one that used the indicator is starch. Blue black to colorless. Okay, so calculate the moles of iodine in the solution. We've been given the volume of, we've been given the C of concentration of, given the concentration of sodium disulfate, so N2S2O3, we've been given the volume of N2S2O3. Okay, so what we can do is the amount of, we can work out the moles of sodium disulfate, right? We're going to work out the moles of this, so N2S2O3. That will be CV, right? So we know that. We know the concentration. It's 0.2 times 12.75. That's centimeter cubed, so we have to divide by 1,000, obviously. Right? So that's the moles of. So 0.2 times 12.75 divided by 1,000. That is 2.55 times 10 to the power minus 3 moles. But this is the moles of sodium disulfate. You can see here this is a 1 to 2 reaction molar ratio. Sorry, 1 to 2, right? 1 to 2 molar ratio. That means that whatever moles we get from this, to get iodine, to get the iodide, get the moles of iodine, so we have to divide by 2 moles of iodine. So mole of iodine will be this answer divided by 2, so you'll get 1.275 times 10 to the power of minus 3 moles. Alright, so that's that. Move on. Use your answer from II and the equation for the reaction between Cu2 plus AQ and IA minus AQ to calculate the concentration of Cu2 plus in the original sample of solution. So let's go back. So they're asking us to find the concentration of this. Now we know that 10 centimeter cubed could have only provided this aqueous iodine, right? Now because this liquid, and because only this 10 centimeter cubed of Cu2 plus ions could have caused this, this means that the moles of iodine should equal the moles of copper. So moles of iodine should equal the moles of Cu2 plus. That means we can find out the concentration volume. So we know this is what, it's 1.275. So we know it's 1.275 times 10 to the power minus 3 moles equals what? We need to find concentration. So concentration times volume. We know what the volume is. Volume is 10 centimeter cubed. But we're dealing in dm cubed, so we have to divide it by 1,000. Alright, so we have, so this is 10 divided by 1,000, 0.01. So we know this is 1.275 times 10 to the power minus 3 equals 0.01 V, so this is 0.01 dm cubed, 0.1 C. So C is, the concentration is 1.275 times 10 to the power minus 3 divided by 0.01. And we should go what? 0.01, and we get what? So 1.275 times 10 to the power minus 3 divided by 0.01 is 0.1275. Now we also need to go back to the molar ratio. You can see here that one of these iodine gave 2 of these, right? That means our final answer should be times by 2. So we should get 0.255 mole per dm cubed. So I stated that earlier. Okay. Now give your answer to 3 sig fig, which we have, right? And justify why this is an appropriate level of accuracy. Now, why do we usually round to 3SF? 3SF is what? It's the least accurate level of measurement used in the calculation. The whole of the solution containing iodine was used in one titration. Explain how this affects the reliability of your answer to III. So this is reliability. Okay. If we use all of the iodine in one titration, how can we conclude our results are reliable? Because we cannot repeat the results again. And because we can't do that, we have no evidence that the results are repeatable. So it's not reliable. It's not reliable. Alright, so that's why. So the answer over here is obviously this and this. For here is that we cannot repeat the results again because they're not repeatable, so it's not reliable. That's the 1 mark there. So draw and name the shape boron trifluoride. So boron only has 3 lone pairs, and if we attach F, and F, it's a trigonal planar with 120 degrees. So then the name of the shape is obviously a planar. If you just write planar, you don't get a mark. You have to write trigonal planar, and the FBF, the angle is obviously 120 degrees. Alright, so ammonia has the formula NH3. Its NHH bond angle is less than FBF is boron trifluoride. Estimate the angle. So we know that N, so we have H, and we have H here. Bonding pair, lone pair. Because this would form a tetrahedral shape, right? This should form tetrahedral shape, right? If something reacts with the lone pair. And lone pair usually is tetrahedral shape has 109.5 degrees. But because we added this lone pair, we have to decrease the angle by minus 1.5. So our NHH angle, right? NHH angle, I'll put it in green, let's say. NHH angle, this angle here, right? This angle here is 107 degrees. 107 degrees. So explain why the NHH, so this is where we came from. So explain why the NHH angle, right, is less than that for FBF. So this is exactly what I was saying. So it's because there are 3 electrons. So let me change the color. So that's because we have 3 electron pairs in the central B atom, right? Boron atom. Whereas, so wait, no. Whereas there are 4 electron pairs in what? Around the central nitrogen atom. So what can we say? So we say that the extra electron pair or lone pair of electron does what to it? It repels, gives repulsion. So that's why HNH angle is less than that for FBF. So the main point you should add is that there are less space. So there's less space, so it repels. So you can say that all of this, so 3 electron pairs inside of the atom, and because there are 4 electron pairs, that means that it kills repulsion, and that's why we have less. It has a smaller angle. So name the strongest intermolecular forces between BF3. Because this is a trigonal planar, right? That means it's a polar molecule. It's a non-polar molecule. So that means it only has London forces. What about name the strongest IMF, or intermolecular force, between NH3? Because we have the H3, obviously this is hydrogen bonding. So our answer is London forces and hydrogen bonding. Okay. C. Ammonia will react with oxygen in the presence of platinum catalyst at 750 degrees, forming water and nitrogen to oxide. What is the oxidation number of nitrogen in ammonia? That's pretty obvious. It's -3, right? It's the valence electrons, -3. Oxidation -3. Why the -3? Because this has a charge of +3 and this has the -3, so the oxidation number is -3. The diagram shows below the distribution of molecular energies in the reaction at 750 degrees. So this is at 750 degrees. They want us to, on the same diagram, draw a curve at temperature equals 500 degrees. So they want us to draw 500 degrees C. Explain what effect this change in temperature would be on the rate of reaction. Now, what's going to happen in this rate reaction? So if we have a lower temperature, right, what happens then? If we have a lower temperature, what can we say? We can say, if we have a lower temperature, on the diagram, right, in itself, the peak should move to the left, shift to the left. So if we go up over here, and then it also should be lower, all the way, so T equals 500 degrees. Now why is that? That is because lower temperature, so we write lower T would mean what? Would mean that the average energy of the particles would decrease. So we write the average energy of particles would decrease. And because we're talking about rate, and as a result, what happens to the rate? We will have fewer successful collisions per second. Fewer successful collisions per second, right? Because that's what we're doing. Per second, the frequency. So the fewer collisions per second, and since there are fewer particles that overcome, so and because of this, fewer particles have the energy to overcome the activation energy. So the rate is slower. So the rate decreases. So the reaction rate is slower. And you can see here all of this in the diagram. You can see here that if I do it now, let me use this. So you can see here that there's a small number of particles now compared to the previous. So previous, you can see here all of this was first included. See here, all of this was here before. So all of these molecules before had enough energy to take part in the reaction, but because we decreased it to 500, we have a significantly less amount of particles. Fewer particles, so fewer, that can overcome EA, overcome the activation energy. So the reaction rate is slower. So what are the marks? You can see that the marks are, so the mark is obviously one for the diagram, and so we have 1 mark for this. So 1 mark for this, that it's lower than this, and 1 mark for the shift in the peak. And then 1 mark is just to say that there's the reaction rate is slower. So if I put here, the reaction rate is slower due to that there are less particles that have the enough energy to overcome EA. And that's because we have fewer collisions per second. So we have to state all of that. Alright? Explain how a catalyst speeds up a reaction. So a catalyst, like by the definition of the catalyst, is what usually provides an alternative route or pathway. So we get pathway. So wait, pathway route that has a lower activation energy. What happens to that? Because we have a lower activation energy, what else? So that means more molecules can react previously than previously, obviously at a given temperature, right? At the same temperature, so at a given temperature. Okay, so the marks are that they provide an alternate pathway and that has a lower activation energy, so more molecules can react than previously. Instead of saying more molecules, you can also say greater proportion. That's also a good way to put it. Okay, so now we're moving on to question number 21. So we have ethanoic acid is industrially used to manufacture polymers and glues, and also in the food industry. It can be synthesized in the reaction of ethanol with excess sodium dichromate and concentrated acidified with concentrated sulfuric acid. So they're telling us procedure. So the concentrated acid is a drop at a time. The sodium dichromate is then added a drop at a time. Mixture to boil spontaneously, so it must be very hot. When the addition of sodium dichromate is complete, the mixture is then heated under reflux. The ethanoic acid formed can be separated from the reaction mixture. So we have this. Okay, so this is one way of getting ethanoic acid, and another way is this. You can see here ethanoic acid can be produced industrially with this Cativa process. Methanol can be obtained from wood, so they're using methanol in the presence of a catalyst and getting this. So balance the half equation for the reduction of the dichromate ions. So you can see here, you can talk about, so this one's pretty simple. So you have to look at this side. You can see there are two CR2, there's two CR atoms. Over here should also be 2. What about the oxygen? You can see there are 7 here. There must be 7 here. That means that 7, this should be 7. And because we have 7 here, we can find out the amount of H plus ions, because 7 times 2 is 14. So 14 H plus here. We have 14 here. And now what do we have to do? We have to balance what? We have to balance the charge. You can see this is only a 3 plus charge here. This is what should be the same thing as, so minus 2 plus 14 plus what we have to take away, right? We have to plus, let's just call this x, right? So this is what we're going to put here. So this is what, x plus 10 equals, so x plus 12, my bad, x plus 12 equals 3. So x equals minus 9, right? So this means that we have 9 electrons here, right? So that means what? So we have over here, do we have 9? No, I don't think we do. Let me double check. Yes, there are 2 of this. This must be 6. Sorry, a mistake here. So this should be, so we have 2 minus here, then we're adding the plus 1 charge, then we're adding, what else are we adding? We're adding 2 minus 2 plus 14 pluses plus electrons, we don't know how many, it goes to 6 plus, right? So that means you have this E minus goes to 6 plus 6 plus 2 minus 14. That's going to be E minus goes to 6 plus 2 is 8. 8 minus 14 is minus 6. So we have 6 electrons here. 6 electrons here. Okay. So that is the answer. So that is the answer. Okay. So half equation is oxidation of the ethanol. Use this and the answer to AI to write a full equation for the overall reaction between acidified dichromate and ethanol. State symbols are not required. So the key thing here is we need to cancel out the electrons. So if I highlight the electrons, so this is 6 and this is 4. So we need to make them equal. So that would be the closest would be times 2 and times 3. So you get 12 E minuses and 12 E minuses here. So let's do that. So that would be times by 2. So that would be 2Cr2O7, 2 minus. And we have plus 28 H pluses. So the electrons are cancelling out. So you'd be so this plus, we have 4Cr3 pluses plus 14 H2O. And we add that to our 3. So 3CH3 CH2OH plus 3H2O goes to what? Goes to what? It goes to 3C CH3COOH plus our 3 times 4, which is 12H plus, and the electrons are gone. So now what you do is we look at the side which has, so look, if you look at here, so you're 28H plus, right? 20H plus, and we have H plus here. Which one's more? It's obviously this one over here. That means we take the 12H plus and put it here. So that would be, so it will be 2Cr2O7, 2 minus, and 28 minus 12. 28 minus 12 is 6, so 16. So this will be plus 16H plus. So that's fine. Or anything else that's similar? Yes, there is. There's 3H2O and 14H2O. That means that the 3 will go to the other side. 3 will go to the other side. That would mean that you're getting rid of 3. So that would be 11. So obviously, and we add plus 3CH3 CH2OH goes to 4Cr3 plus. That's unchanged. Plus our 11H2O plus our 3CH3COOH. So that's our equation. So you get 1 mark for knowing the ratio, for doing this ratio calculation, and 1 mark for obviously the overall equation. Okay. Why are the concentrated sulfuric acid and sodium dichromate added a drop at a time? Now, like I said before, they're added a drop at a time because it's a very vigorous reaction. So we can say it's to prevent the mixture heating too rapidly. That's why. Rapidly. Draw a label diagram of the apparatus shown that could be used to heat the mixture. Now, because it's heated under reflux, we should remember, so I've got this diagram, I'm not that good at drawing, but I've got the diagram, but I'll try to illustrate what you can draw. So you should draw a flask, right? Draw a round bottom flask, which has the Liebig condenser. So if we have, and it must be open, by the way. So you have the Liebig condenser, and you have this. So this you have to talk about water out here, and you have to talk about water in here, and this must be open, by the way. This must be open. And you can say apply heat. And yeah, that's it. So super fast, so round one fast. You can also put in anti-bumping granules, like it's also part of it, but it makes the drawing better. But that's not what they want. That's not all. They just want heat. They want water in, water out, and they want a suitable flask, which we do have, and the Liebig condenser should be drawn properly. Okay. So what color would be the mixture? So we know that potassium dichromate turns green from orange to green when it's oxidized, orange to green. So that's what's going to happen. So it's green. A solution containing both water and ethanoic acid is produced by distillation in the final reaction mixture. Explain why the other products and any excess reactions are left behind in the distillation flask. If we have distillated it, that means that these other products have an excess reactants, must have. So these other products. So just think about simply, must have a high boiling point, because we have applied heat already. Must have a high boiling temperature, right? High boiling temperature. Suggest the method to separate pure ethanoic acid, boiling temperature 118 degrees C from the water. Now, because they've given you the exact temperature they want, the easiest way to do it is to use fractional distillation. When we have a fractionating column, fractional distillation makes it easier to separate anything at a given temperature. In the cadaver process, what would happen when you increase the pressure to the yield of ethanoic acid? So if we go up here to the cadaver process, and we'll just okay, so let's go down. So this is the cadaver process. What's happening here? So we can say increasing. So we can say increasing pressure. We know the increasing pressure favors the side with less molecule, the less gaseous molecules. So increasing pressure would increase the left, so right hand side. You can see over here we have 1 mole, we have 2 gaseous molecules here, so it would favor this, so would increase the yield. The 2 points are that it increase the right hand side, increase pressure would increase the right hand side, so it would increase the yield. Okay, so just two reasons why it might be difficult or undesirable to produce ethanoic acid by scaling up the laboratory process. Now in the laboratory process, we know that the yield of lab process can be very low. And what else can we talk about with labs? We can talk about what? We can say what? We can say what else can we say? What else can we say? If we want to make this into a lab, right? The laboratory process, if you go back up, it's this one. It's this one over here. It's the ethanol with the excess sodium dichromate, right? Excess sodium dichromate. Now we know that sodium dichromate, which is acidified with concentrated sulfuric acid, it's a very toxic oxidizing agent, right? So this concentrated sulfuric acid is, and the oxidizing agent is very toxic, so not suitable to produce by scaling up the lab process. You can also talk about the lab process has a lower atom economy. You can also talk about the cost of the oxidizing agent and how would we dispose Cr 3+, right? You can talk about the yield is low and that it's very toxic. That's what I've talked about. You can also talk about that the lab procedure is a batch process. You can't instantly make it and keep making it. You have to wait and then get more resources and try again. Okay, so we have E, an alternative industrial process for the production of ethanoic acid in the oxidation of butane using a transition metal at 150 degrees C and 55 to 60 atmospheres. Evaluate the greenness and sustainability of 2 industrial processes, and then suggest 2 additional pieces of information that would help you make a more informed decision. So 2 that would help you make a more informed decision. Okay, so let's just compare. So we have, okay, let me try again. If I go here, and I can, yeah, that's fine. I can remove this. Okay, So this is the thing. So this is the Cadiva process, and we're trying. So it's very important that we compare, right? So let's look at what we can compare. Let's look at the temperature first, right? So you can see that what the Cadiva, right? The Cadiva process. What the Cadiva process? What about it? The Cadiva process runs at a higher temperature. Runs at a higher temperature. So what? So what? You need more energy, right? So greater energy is required. Greater energy is required for heating. What else? Compared to the obviously the alternative. What else can we say? You can say that the Cadiva process, right? Process runs. You can look at the pressure. So 55 to 20. So 55 to 60 compared to 20 to 30 runs at a lower pressure. So less energy is required. For what? Required for compression. What else can we compare? What about the products? Let's look at the products. You can see here this only has one product. This has two products. So you can say the Cadiva has what? 100% atom economy, because we only have one product. So compared to the alternative. What else can we talk about? And because it only has one product, right? One product. What else? I mean, there is not much separation required, and not much separation required. So if I go back, separation required compared to the alternative process. Okay, so so I think that's 4. So just 2 pieces of evidence. It's the information that will help you make a more informed decision. If we found the yield, right, the yield of both reactions, then that would help us greatly. So if we knew the yield of both reactions, what else can we talk about? If we have the yield, what else can we talk about? We know that this uses what? Methanol, right? And we need to find out how renewable it is and how available it is, right? You can also talk about how available butane is. So you can say, if we knew the yield of both reactions and the availability of methanol and butane would help us decide better. So that's the answer. So what are the key points? So you can say that Cadiva process runs at a higher T, so more energy is required. It also runs at a lower pressure, so less energy is required for compression. What else? Zero compression. Okay, what else can we say? We can say that Cadiva has 100% atom economy because of one product. What else? And because it only has one product, right? We require less separation. Right here, since only one product. That's why. Okay, so that's the end of the video. I hope you guys enjoyed it, and please like, share, subscribe, and join the Discord. I'll put a Discord link where I upload all the solutions, and I'll see you in the next one.